Lizzie was on the fence already because Colin, her brother, was on the fence. So I think if we could get both of them, not necessarily put them on the same team, but Lizzie could be on the A team, and Colin could probably be like our B team leader. That was Worthington local. This is our regional that we go down to Columbus State for. I mean, the local scrimmage is just, we just do it to get comfortable with stuff.
But they just do it because right now, right?
But let's talk about that stuff later. So keep trying to convince people. Is really all I can say. I got free shirts. That got some other attention. Really? Yeah, I have more shirts back there, but I have that stack also. Are you going to come to Math Counts on February 8th?
Yes, you will. Yes, you will.
Guys, everybody in this class would be great to come.
What if we
The
all
shirt
go
that might
together?
actually convince you.
What if we all go together?
Well, only 4 of you could be the team.
Oh.
So then I won't go and you guys can go.
Okay, I'm good with that.
Wait a minute. So you want to be
David,
Yeah, I
look at
want
this.
to be helpful.
Tell me that you don't want this shirt.
Oh my gosh.
Is that Star Wars? But
Are you not into Star Wars?
no, I mean yeah, but it's just very punny, and I like that.
I know.
Oh
Right?
my gosh, I
And then the other ones are the be greater than average shirts, all the red ones.
I want to be.
February 8th.
Can I still get a free shirt if I don't go?
Nope. You gotta come with us.
Can I get the shirt now?
Nope. Oh, sure, but you gotta commit to going.
Just get the shirt.
Alright.
Can you two come with
We
me?
I'll do it.
are gonna build. You wanna go? You wanna go to Math Counts? Coming? Next Saturday?
If Athena goes, then I
Wait,
guess I'll
it's
go.
it's next Saturday.
Yeah, February 8th. Not this Saturday, but next.
And then I think I got stuff this weekend, but I'll look.
This weekend, not next weekend.
No, I got stuff like every weekend. And if I don't have stuff, then my mom wants me to move boxes.
Won't be helpful.
So
Yeah, you will.
What?
Your math skills are pretty darn strong.
wait,
Are
what
you
time
doing
is
it
it
now?
on
I
Saturday?
said I'll go, but I won't be helpful.
Oh, well then I'll go with Athena and Cynthia.
Leanne, you going?
No, I have indoor soccer every Saturday too.
What
I like
time
soccer,
is
so I
it?
can even
Wait,
Rob, we'll leave here at like 8 in the morning. We
Wait,
take a
what
bus
time
down to
is
Columbus
it?
State. We'll be back at like 3.
Yeah, I think I have a futsal game then too.
Wait, can I do the times?
If you guys have any extras or there's handout, I can print more of the info sheets on out.
I mean, I still have one in my mind.
Yeah, if you have an extra one, you could give it to David.
Die.
Hey, this is panning out well.
It's the shirt they got me.
What if I give you guys like a free mastery?
Wait, give us the rest of those ice cream sandwiches.
I already gave those away to Math Counts during a Math Counts meeting.
Darn it, we've been betrayed.
No, if you had shown up to Math
Can I
Counts.
theoretically go to math counts but do my math homework because I'm still doing math but it gets
But it counts.
Yeah,
And
but
it
Yeah.
counts.
I'm not even that worried about if people have come to Math Counts during extensions, because that we just do like little exercises then. I'm just trying to get people to go with us to competition.
I don't even know.
So I can come during extensions today and get the snacks but just do my
Sure, but I got to try to get some more snacks because I'm running out of stuff.
Ooh.
All right.
Things like regret.
Can we have our class lesson? Because now we only have like a half an hour.
Oh yeah, sure.
So we're gonna play the amazingly exciting game, Build a Farm.
Only with that
Woo! I think they were writing this when Farmville was really popular. It was an app where you would build farms. So that's how quickly apps come and go. So each player first spins a spinner. Half the spinner's red, half the spinner's blue. Ooh, ah. If the spinner lands on red, the player reaches into the red box. If the spinner lands on blue, the player reaches into the blue box. Pretty straightforward rule so far. Red box has 10 chicken counters, 10 pig counters, and 10 cow counters. Blue box has 5 chicken counters, 4 pig counters, and 1 cow counter. Draw a tree diagram, including, guys, tree diagrams are the best way to represent situations like this, including the probabilities to represent the entire sample space for this game.
Okay, so go from red to blue.
Wait, so if you spin like blue, do you just like pick one of like the animals?
Yeah.
Do you
So,
pick,
hey,
like,
before
all
I
the
scroll down,
animals?
we have 10, 10, 10, right? Chicken, pig,
Wait, 10,
cow,
10, 4 to red one, right?
or 5, 4, 1.
10, 10, 10, and 5, 4, 1, right?
So, one branch that goes red is going to be kind of like the fair branch, because they're all even. Now, what's our chance of getting red?
50.
1/2. We want to do probabilities and fractions. Then, for chicken, pig, or cow, what are the probabilities of those? 1/3, 1/3, and 1/3. What?
Oh, I went to the College Credit Plus thing.
And they kept saying CC
Oh
plus,
yeah,
right?
They
My
say,
mom
kept on
went to
saying
that.
CCP, and I kept on thinking CPCTC.
It was very funny. CCTC sounds like a sad mystery.
Wouldn't it make sense to use a different variable for cow?
Why?
Because it's CC.
Oh,
So, like,
ah.
we can do W cow.
What is the W again? It's almost CPM, you guys. The cow is actually just.
What's our chance of chicken?
Is that our cow? Is that our chicken?
Or we could do an input cow.
Ooh, 5 out of 10. So yeah, 1/2. So you were right. I was just wanting the unreduced first. So 5 of our 10 possible options, or 1/2. Pig,
2/5 or 4/10.
4/10 or 2/5. And then 1/10. So now we can use the tree diagram to talk about what's the chance of getting a cow given you got blue, or just what's the chance of getting a cow.
Which one do you want?
Right, so wait, if we talk about all of these outcomes, we can talk about like red chicken, red pig, red cow, blue chicken, blue pig, blue cow. Question before we keep going on?
Never mind. It wasn't a question. Whatever.
So, what is the probability of getting a cow?
Well, since we know that no matter which one, red or blue, it doesn't matter because they both contain a cow.
No,
Ooh.
1/20 is white because
Yeah.
one
Ooh, so down at the bottom here, we can write the actual probability of getting that result. So getting this chicken result is 1/6 because it's 1/2 times 1/3.
Well, aren't we doing cows, not chickens?
I know, but we're going to do all of them. So this is also 1/6. This is also 1/6. Over here, 1/4, 2/10, or really reducing down to 1/5, and 1/20. So then if we talk about what is just the probability of getting a cow,
It's 1/6 plus 1/20,
1/6 plus 1/20.
and I don't know what that is.
Wait, but it's no matter.
6.5/30ths,
Wait, hold on.
which will be gross, so 13/60ths.
We're
I think
doing
60
it 1/2
is the lowest.
times 1/3 and 1/2 times 1/10. But we know that no matter red or blue, we're getting a cow. I mean, like no matter red or blue, there's a cow in each one.
Right. So we're saying in general,
Oh.
when you play a turn, what's the chance of getting a cow? And you could get it 2 different ways. Right, so we're adding the probabilities of the 2 ways that we could get it. Now, for those of you that think an area model is better, here's what we would need to do when we draw an area model of this situation, and you may copy this if you want to, or you don't have to, because I like you guys, and I'm not going to make you do things that aren't 100% necessary. But where is this slightly more advantageous than the tree diagram? Yeah, we can visualize because this is like an area model, right? So the area of things, you're fine, dude. That's all you needed was like 3 seconds. Actually, that was like 1 second. So the area of things helps us relate the probabilities. So we can see this chicken's probability is actually smaller than that chicken. This pig's probability is actually smaller than that pig. And obviously this cow's probability is bigger than that cow because there was only one cow counter in the blue bin. So now it brings up this other question. If you know that a player got a cow counter, what is the probability that that player had originally spun red?
Wait,
1/6.
wait. If you know a player got a cow, what's the probability of 50%, right?
I'm confused by the question. Can you restate it?
If you know
You're all
the player,
talking at the same time, and it seems to not be working very well. collaborate together. You don't even need to pick people to talk. Just have like social norms.
If you know a player got a cow, then what's the probability that a player had a red spin?
Okay, so there's a 13/60th probability that they got a cow.
Yes.
And so the probability of red and blue is 1/2. So it's the probability of red when you know that you got a cow.
Oh.
How would we write P of red given cow
So wouldn't that be
in
like
a better manner? We
wouldn't
talked
it-
about how we write it yesterday.
Cow.
Hold on. How do we write this on our paper? Because we don't want to write the word given.
it was
The line, right? The vertical line. So what you should have written on your paper right now is P red vertical line cow. And we talked yesterday about that vertical line kind of acting like our,
denominator.
well, like the fraction line, which makes the thing that comes after it the denominator.
50% divided by.
One
That's not 50.
1/2 over 13.
Yes, 1/2.
No, there's two possibilities. But they're not
Red.
the
Yeah. Okay, look. Red and blue have the same probability, even though
same.
they're
But
two
cow
probabilities.
and
I'm going to give you guys a couple minutes to talk about
I'm
it.
not talking about
I'm
cow. I'm
I'm
talking about
very
red.
confused because people keep saying different things.
Well, maybe one person should share their thoughts and then we can go to the next person. I don't know. That's just an idea.
What's the probability? Oh, because there's a higher probability of getting a cow and red. Oh, I get it. Sorry, I was confused.
Now I'm very confused. So you said something and you said something. And then
So the reason why the probability of getting a cow in red is bigger because you have a higher chance of getting a cow in red than getting a cow in blue.
Yeah.
You get it. Sorry, anyway, you have a 1/10 chance of getting cow in blue and 1/3 chance of getting cow in red. You have a higher chance of getting a cow in red.
yeah.
So that's why the probability of getting a cow in red is higher than the probability of getting a cow in blue.
Yes, but we need to find the probability.
Yes, but I was just, I thought you were confused on that part.
No, I thought you were talking about how to find it, and I was confused
I
about
was
how
just,
to.
yeah, that was right there.
Alright,
Yeah.
let's add them together.
If we're speaking in terms of given cow, which sounds funny,
Given cow. You got red.
then the space we're looking at is just the cow space.
Okay.
The thing we want, the event, is red out of all cow, which is red cow, blue cow. Sounds like a Dr. Seuss book.
One cow,
So-
blue cow, red cow, blue
so-
cow. What do you want? We all want cow.
Is getting red and getting cow... Are getting red and getting cow independent of each other?
No.
Why?
Probability of getting cow in red than getting cow in blue.
Because what?
And there's a different probability. It's 1/3 cow in red and 1/10 cow in blue.
Because they're not the same, they have to be dependent instead of
Yes.
independent.
So you guys were saying when we talk about probability of red giving cow that we're gonna have like some probability over some probabilities, right? Didn't you say like I heard you like I was listening to you guys while I for a moment just didn't say something. You were talking about like we're gonna have like 1/6, right? Didn't you? Because that's the probability of a red cow
Yeah.
over what?
1.
120 plus 1/6.
1/6 plus
So
1/20.
1/26.
Hmm.
Something
No.
was correct.
It's, I did it earlier. 13/60th. 13 over 6 is the 1/6.
13 over 6.
No, for the bottom one.
I have a feeling this could be a lot simpler.
This is why I don't like cows.
Oh, we want. What?
This is turning me vegan.
Can I try something?
Of course.
Well,
Ow!
put it in.
Sorry.
Go ahead. Then I have a thought.
Well, so like, couldn't you just do like the total count? So the number of red cows over the total cows, or is that?
Yeah, weren't there 10 chickens here?
Yes.
And 10 pigs here?
Yeah.
And 10 cows here? And then weren't there 5 chickens here, 4 pigs there, and one cow there.
So couldn't you do 10 over 11?
Is it 10 over 11?
No. 10 over
Wait, if you know.
There's 30 tokens here, right?
Yes.
So cow is 10 of 30.
Yes.
But there's only 10 tokens here.
Yes, so go left.
So it's like cow is 3 out of 30.
So really, we need to think about this as 15,
Well, what just happened?
12,
Wait, what?
and 3
to
to
make this
make them the same size.
We just multiplied it.
So it's like
Yeah.
13.
Because we
So
want
10 over
30 tokens over here as well.
10 over 13 then.
Okay.
It's just an equivalent fraction, right? So now we have 3 over 30 instead of 1 over 10. But this was 10 over 30, right? Of the 30 up here, which I should really be boxing in red. But of these 30, cows were 10. Of these, now 30, cows were 3. So this is actually 10 over 13.
Wait, what did you say?
10 and 3.
'Cause the
Not
probability-
10 and 1. We have to do 10 and 3 once we make these sample sizes the same size.
And the okay, so probability get a red cow over probability red cow plus blue cow.
The entire cow space. Yep.
That's okay. Okay, I get it. Cow. I don't know if you guys get it, but
Now you could also go even further up. You could actually do percentages if you wanted to do that, or do rate values.
I did the actual math on the calculator, not saying
I did
With the-
actual math.
with the 6 and the 20.
So should this be more or less than a half? More, obviously, because this space, the red cow space, is obviously larger than the blue cow space. So obviously my probability is going to be closer to 1 than it is to 0.
Red cow space is just a.
Yes. Well, have you ever seen a cow field?
Well,
They're really, really big.
there's just blood on the.
Do you know what a cow pie is?
No, I don't.
Cow pie is cow poop. And it's all over the cow field, and it smells.
Yeah.
They hire someone.
Oh, is that, I remember we did like.
Oh my gosh.
So try this. Hold up. What is the conditional probability? Careful. This turns things around.
Conditional.
What is the conditional probability that if you got a pig counter, sorry, I shouldn't have said this turns things around, but it's phrasing things differently. If you got a pig counter, your spin was blue.
So we know that we got a pin.
12, 24.
12 and the 10. So, yeah, what did you say?
So,
Oh, yeah.
wait, how did you get
Because the 12 plus
two
4.
fours?
Well, shouldn't it be
12.
Yeah. How did you get 24?
Wait, 12 over 22.
Yeah.
No, it's not. That's not.
12 over 22.
12 over. Yeah.
12 over 22.
You said 24.
I know. That's
It's
what I was.
okay. That's where we got confused. Because we're all like, wait, Sophia's always right. How'd she get 24?
Sophia's gonna.
So yeah, 12 over 22, right? The conditional probability is changing what sample space we look at, right? So that's where conditional probability is messing with what we've done before. So now we go to the next booth, right? We're not really into that whole making farms. So we go to this booth that says flip, to, spin, or roll. And you're like, okay, lots of words. Sounds fun. So
You know, we talked about crabs yesterday. I just came on with mine.
What? Yeah, you didn't get the dice. We saw it.
Oh no.
I start a timer with my 3D class when they jump way off topic, and I just have to sit and wait, and then they give me that time back during their break. I don't want to have to do that with us, but I don't know why you're talking about crabs.
Crab.
Carbs? What did you
I said
just say?
crabs.
Crabs? Oh, yeah, okay, crabs. Yeah. Sorry, I heard you say crabs.
That's what I heard.
Like, we did not talk about crustaceans yesterday, especially
I'm pretty.
So if a heads comes up, the player gets to spin the big wheel. Ooh, the big wheel. It has 10 equal sections, 3 red, 3 blue, and 4 yellow. If the coin comes up tails, Sonic sidekick, the player gets to roll a cube with 3 red, 2 yellow, and 1 blue side. If the player ends up with blue, that player wins a stuffed animal. Anything else, you get your toenails ripped out.
That's extremely painful.
So, no, just nothing happens. You lose your mind. So, draw a diagram to represent the situation. I don't care if you go tree diagram or area model, represent this situation, and then, supposing that Tyler won a stuffed animal, then what was the probability he started off by flipping heads? So essentially, what's the probability of heads given a stuffed animal? And the given stuffed animal, what's that actually mean? Crap, that's not blue.
Wait, so they don't win anything if they get heads, right?
Well, they might. If they get blue, they win.
Oh, if you get blue.
If you get blue, you win. If you get blue, you win.
Oh.
Mm-hmm. Gotta go back and careful read. I'm gonna need to get a different pen for this smart work because this tip is getting all beefy.
You got 2 on this.
I know, but I feel like they all are. So,
Yeah, I think I used that one more.
what's our general consensus? Tree diagram or area model? Area.
Oh, I wanted to say
Already
tree.
tree. I did a tree because you said to do tree before, so I gotta do it again.
I mean, so we start off with half and half, right? I mean, equal probability to start.
Right.
If we want to do area model, I'll go ahead and just, use a box. 3 red, 3 blue, 4 yellow.
What's the coin one? Not the coin.
The coin was heads.
I know the coin,
right,
but
and
what was
tails.
the die?
It's still up here. You should still be able to read that.
Wait, do I change mine to an area?
Oh, never mind.
I was like,
Wait, should I just change it?
Tails, cube is 3 red, 2 yellow, 1 blue. One technique some people like to use is if you know how many sections there are, go ahead and split your sections first. And then we could say 3 red, 2 yellow, 1 blue, right?
The lowest color you could get is the lowest chance of color
So
you
you
get.
blue, you kind of lose.
No, if you got blue, you win.
No, I mean, if you tail, you lose.
Why?
well,
It's hard to get.
if it's
Yeah.
tail, it's not very likely.
Yeah, but still, even in heads, blue is technically.
So you'd want
3
to
red,
get a
3
head.
blue, 4 yellow, 3 red, 3 blue, 4 yellow.
You know what? They'll probably get like a coin that's both tails and then a die that doesn't have any blue on it. So then, like, you always give them money because they don't like giving away colors for free.
Even unfair.
Even if you pay for it to play, they're like, oh no.
Thanks for the money, too. Stuffed animals like worth half the money you actually spend to play.
Oh yeah, that's true though. Stuffed animal is probably worth like
$5 when you pay 10.
yeah.
Mark Rober has an interesting video on that.
I just knew that. I thought that was just basic logic. The price you get is probably worse than the money you pay.
So if all of these
They
are
want to make
together,
money even if you win.
Exactamundo.
I should just erase.
And those yellows are together.
Yeah, and those yellows are together.
Why didn't you erase?
So this is like a 1/2,
We're gonna play pickup sticks.
and this is like 2/6 or 1/3, and blue is 1/6.
Blue is the smallest one.
Yeah, well, because they don't want you to win. Tyler won a stuffed animal, which means that he had to have gotten blue. What is the probability to start off by flipping heads? Higher probability.
9 over 14.
What is a common denominator that we kind of can use here?
30.
30? Okay, so this becomes
That's 9.
9 of the 30 spaces we're talking about.
And then down on the bottom.
Oh yeah, we should
another
probably.
blue, it's 5.
Oh, then you
So
got
out of
30.
14 possible.
No, wait, so is it 30 or is it 60? Because that one half.
Sure. Well, if it was 60, it would be 1860 and 1060.
So
but
if you factor in the 1/2, then like for heads, the tails would be 320. Yes, and I mean the heads would be 320, and the tails would be 112. So then
Right, or we could say like 9/60ths, right?
Well, I mean,
If we factor in that half.
and then you need to do it for the other one.
But I mean, think about the tree diagram, right? Didn't somebody say they were going to go tree diagram? At the bottom of there, all of those probabilities had to add up to 1. Up here, if we talk about these probabilities, we're actually going to add up to 2.
then it would be over 60.
Right? So if we actually go back, this is really in the whole situation. This red is really 3/20ths. Because it's 3/10 of heads, but in the entire situation, it's 3/20ths. Making this also 3/20ths or 9/60ths. Are we with me on just... Because now we're talking about the whole thing actually has 60 parts to it. This would be 4/20ths if we just want to write it that way. Actually, I'm going to write it like over here. And if this was... So, the top section should be 10 of my 20. Right? 4, 3, 3. I get 10
Yeah.
of my 20 total possibilities.
Yeah.
So then the blue on the bottom would be like 3/18, right? And then the blue one. No, that's not right. Never mind, because you have to multiply it by something bigger to be like to get it equal to 60. So then you could like.
Hey, David, stop listening.
Never mind.
No, I'm listening to you, but David was whistling. My brain could not
You
focus.
have to multiply it, but you have to multiply it. It'd be 10/60ths because you want the 60ths, or the denominator would be the same for both these.
Yeah, this red's actually a 4th, right?
Yeah.
It was a half on the tails, but if we compute it, it's really a 4th.
Actually, never
So
mind.
it's
I was thinking
5/20ths. If we make the whole thing 20. The yellow... Oh, 60 would be better. Okay, so this is what, 20? No, not 20/60ths.
I did it wrong. I was
What would this be?
that-
10/60ths.
Yeah, I was
right?
thinking that was the blue.
Because we have to do the half multiplication. This becomes 2/12ths, and we can get to the 10/60ths. And this becomes
10.
not 10/60, 5/60ths. Because we're computing the actual probability of them.
So it'd be 5/60ths and 9.
So what would the rest be? The rest would be
5/20.
Wait, I thought we were going.
It was 1/2, but when we multiplied by the other 1/2, we get 5/20ths, 10/60ths, because it doesn't reduce nice,
Well,
and 5/60. Well, this one could, but
yeah, I was gonna say.
it doesn't get to 20ths nicely, because we divide by 3. But, all of this to say, if we add up all of these numerators now, the this, and this, we should get 60.
Should.
But since we're looking at assuming he won, we're looking at just this region and this region,
So many.
which has how many pieces in it? 5 and 9. 14. No.
No, because that would not.
So the probability of getting blue is 14/60ths. Yes.
But it has 14.
But we're conditional here. We're saying what's the probability of having flipped heads given that we won a stuffed animal? 9 14ths, because we have 14 total sections covered by blue. 9 of them came from heads. So this would be 9 14ths.
Or if you were just talking about blue,
Questions? Now this is one of those situations where honestly tree diagram might have been cleaner. Just because we had so much chaos going on here.
yeah.
And here's the other reason why tree diagrams can sometimes be nicer. You can watch the math happen as you go down the tree. So you can see the fraction on the branch and then multiplied by the next fraction on the branch. You just see the math happening. Here it's a tiny bit harder to see. Anyone have any questions left on this one? How we figure out that conditional? We first need to figure out how much of the space is blue, because that's going to be our denominator, and then go from there. All right, try this. I'm going to try to give you a minute to do this on your own. I will color code things just to split up the information.
Senior class.
Oh, yeah. I thought that was
Hey, David, do this problem.
Wait, just
As soon as everybody, but as soon as I give you something to do, David's like, hey, remember 3 weeks ago when that person at that place did the thing on the thing?
It's all out of 200.
Oh, wait. That goes with that.
You could highlight that it's out of 200.
So does that mean like
Should we use the little diagram that it gave us?
Mm-hmm. Where did my 78 go?
The totals.
all in car?
It's not even in the table.
No, yeah, it'd be
Outside
like
of
car and then
So then what goes here?
200
Yeah. So 1.
so wait.
You guys are supposed to be faster than me.
Wait,
I was
wait a minute.
I didn't realize what you were asking and then you had already started to write one.
Where's 54?
Have regular chores.
Oh,
So
also
it's
out of the
chores,
table.
54. So that means 146. I was close.
Wait, I thought you were right.
Look, at the point
I
when I could do
was.
math
I like
faster,
he wrote it and I
at
said
the
it.
point when I could do math faster than Mr. McCully is when I really felt like, yeah, that's what I want you to get to. You can really beat me. There you go. Which you, by the end of the year, you should probably.
I just have
Because we are
to think.
That's okay. It doesn't mean like good or bad. How long it takes you doesn't really make a difference. Where's that 80 go?
No car, no chores.
No car, no chores. I'd rather have a car and do chores.
No car chores is 42. Cars and chores is 12, and car and no chores is 66.
So there are 66 kids that have a car and don't even have chores to do.
That must be nice.
What
Maybe
in the world?
they have a car, so they're going to college credit plus. So they can drive to college.
I'd be the one that would have like no car and chores.
It's definitely like magnetizing.
Giving them a benefit of the doubt.
Probably be the car.
Car insurance.
Question? All right. So now we get to the analyzing of
We
that.
should do one that has like who has a license and who has a car.
How could we answer this question?
Yes.
We have to support it with data.
Figure out
If you
like
say yes,
car
then
percentages.
Yes or no?
So if you have a car and you have chores, that's a 12 out of 78.
Could we figure out the probability of having a car?
Yeah.
Let's do that real quick. Just write things down that we know. P of car. What is it? How'd you do that?
I split 78 in half.
Or you could just do 7.
78 out of 200.
It's 39.
So 39%.
Oh.
What's the probability of a car given chores?
12 over 78.
12 over 54.
Wait a minute.
I like how
You have a
I
car
given
given, I
after
got
I did
four.
it divided.
Oh, wrong side. I was
Twelve
That's
out of
4 over
50.
18.
Wait.
Because 54 divided by 3 is 18.
Well,
No, it's not.
Doubling this would be over 100.
It's
Doubling this would only be 24.
2 over 9.
Are these going to be equal?
Isn't it 6?
No.
Is it 6 over 27?
I mean, it could be, yeah.
Oh, well.
I mean, but that's not really that
so
nice.
2 9.
What's this as a decimal?
0 point.
2
0.2 repeating.
2 9.
So, wait. The probability that you own a car, given that you are assigned chores, is less than the probability you just own a car? Hold on, let's flip this question around. What's the probability that a student has chores? Write that down real quick.
54 out of 200.
27.
So we're like 27%, right? So the probability of chores.
Key chores is 27%.
What's the probability you have chores given that you have a car?
It's 12 over 78.
One, like 0.1.
0.1553.
15.4%.
Yeah, 0.15.
Whatever.
So the probability that a student has chores is 27%. But the probability that a student has chores, assuming they have a car, goes down?
Wait.
Don't laugh. Like, this is data. We don't laugh at data. Right? What could this mean? Why would this make sense?
When they have a car,
One person at a time, David.
when they have a car, they probably have to use it to go to places or do things, or maybe get a job. They have a job now, or maybe they're taking extra classes.
Athena.
Maybe forgot what I was gonna say. I was gonna say they're too busy doing the chores.
Too busy doing it. Oh, so you're saying if they have chores, they don't need a car because they're busy with chores and don't have their own car. And David said kind of the flip thing. If they have a car, they're busy away from the house and don't have time for chores. So what else makes the difference between if you have a car or not?
Parents.
Legally.
Oh,
Well,
age.
Age.
Oh.
Do you think that as you get older and your academics become more difficult, your parents may give you less chores to do? Yeah, I mean, if they're really academically minded, then, you know, if you've got a giant essay to write and they're like, take out the trash, like, your essay is probably more important, potentially. So, hey, where are you going? Well, I guess we're out of time. But yeah, so guys, this shows us that these events are not exclusive, right? These events relate to each other. Having chores relates to having a car. Having a car relates to having chores. Any way we look at it, they're related because they change. Remember, these then are dependent. The last thing I want to make sure we know is the definition of mutually exclusive. Mutually exclusive also means disjoint. Read this for a second. Mutually exclusive means if one of them occurs, the other one cannot. So the probability that you are in band and digital art is 0. You cannot be in band and digital art, right? You can't. But the probability that you're in band and choir, that probably, like, you can do that. So, mutually exclusive. Hey guys, hang on just a second. In the past, the confusion was that mutually exclusive meant independent or dependent. It's not. Mutually exclusive literally means they cannot exist with
So
each
they
other.
can be independent or dependent of each other, but they just can't happen both at the same time.
Right. So I mean, the probability of the and situation is 0. They cannot happen together.
So like if you have like math first block, you can't also have connections.
Yeah, that's what we're saying. Yep. All right. Thank you very much. Have a good day, guys. Or like the probability I vote for a Republican president and a Democrat president. Like you can't do both.